Reference current generation using synchronous reference frame theory. The integration of renewable energy sources and the proliferation of nonlinear loads in modern power systems have led to an increased focus on power quality enhancement techniques. One of the key challenges in power electronics and control systems is the precise generation of reference currents to compensate for harmonics, unbalanced loads, and reactive power in real time. The synchronous reference frame (SRF) theory, also known as the DQ0 transformation, provides an effective and accurate method for generating reference currents, enabling the implementation of advanced control strategies in power electronic systems. Reference current generation technique. The SRF theory involves transforming the three-phase quantities, currents and voltages, into a two-dimensional rotating reference frame, the D-axis, direct axis, and Q-axis, quadrature axis. These axes are aligned with the fundamental frequency components of the system, simplifying the analysis of the system's behavior. 1. Signal transformation *. The three-phase currents and voltages are transformed into the DQ0 frame using the SRF theory. This transformation separates the fundamental frequency components, D-axis, from the harmonic and reactive components, Q-axis. 2. Harmonic and reactive power extraction * by analyzing the transformed signals on the Q-axis, the harmonic and reactive power components are extracted. These components are essential for determining the compensation needed to improve power quality. 3. Reference current generation * based on the extracted harmonic and reactive power components, reference currents are generated on the D-axis and Q-axis. These reference currents represent the compensating currents required to neutralize the unwanted harmonic and reactive power in the system. 4. Control implementation * control algorithms such as proportional integral (PI) controllers or more advanced techniques like model predictive control (MPC) are employed to calculate the actual compensating currents based on the reference currents. These compensating currents. Hysteresis controller, precision control for power electronics. In the realm of power electronics and control systems, the hysteresis controller stands out as a robust and effective technique for maintaining stable and precise control over various devices. Hysteresis control is a nonlinear control strategy that provides a simple yet powerful method for regulating systems, especially in applications where accuracy and responsiveness are paramount. This controller is widely used in power converters, motor drives, and other applications requiring real-time adjustments to changing conditions. How hysteresis control works. Hysteresis control operates based on the concept of hysteresis, which refers to the phenomenon where the output response of a system depends not only on the current input but also on the history of past inputs. In the context of power electronics, hysteresis control compares the actual system output with a predefined reference value. If the output deviates from the reference, the control action is triggered to bring the output back within the desired range. The hysteresis band, representing the allowable error margin, determines the width within which the system can fluctuate without triggering a control action. Advantages of hysteresis control. 1. Simplicity and robustness * hysteresis controllers are inherently simple, making them easy to implement and understand. Their robustness to noise and disturbances in the system makes them suitable for applications where reliability is crucial. 2. Fast response * hysteresis controllers offer extremely fast response times. When the system output deviates from the reference, the controller takes immediate corrective action, ensuring rapid adjustments to changing conditions. 3. No oscillations * unlike some other control techniques, hysteresis control does not produce oscillations around the desired setpoint. The on-off nature of the control action eliminates the need for proportional or integral terms, simplifying the control design. 4. High-precision * hysteresis controllers provide a three-phase voltage source inverter (VSI) is a key component in modern electric power systems, playing a vital role in various applications such as motor drives, renewable energy systems, and industrial automation. It is a power electronic device that converts direct current (DC) power into three-phase alternating current (AC) power, enabling the precise control of voltage, frequency, and phase angle. The three-phase VSI operates based on pulse width modulation (PWM) techniques, allowing for efficient and flexible control of AC motors and other electrical loads. Operation principle ***. The basic configuration of a three-phase VSI consists of 6 power electronic switches, typically insulated gate bipolar transistors (IGBTs) or metal oxide semiconductor field effect transistors (MOSFETs), arranged in an H-bridge topology. The switches are controlled by PWM signals to create a simulated sinusoidal output waveform. By modulating the width of the pulses, the VSI generates a finely controlled AC output voltage, which can be adjusted to match the desired frequency and amplitude. Advantages and applications ***. 1. Efficiency and precision ***. Three-phase VSIs offer high efficiency due to their ability to control the output waveform precisely. This precision is crucial in applications where accurate control of motor speed, torque, and direction is necessary. 2. Regenerative braking ***. In motor drive applications, three-phase VSIs can operate in regenerative mode, allowing them to convert excess energy back into the DC supply, improving overall energy efficiency and reducing heat dissipation. 3. Variable frequency drives. VFDs three-phase VSIs are commonly used in variable frequency drives, enabling the control of motor speed and providing soft start and stop functionalities. VFDs find extensive use in industrial pumps, fans, compressors, and HVAC systems. For renewable energy systems, three-phase VSIs are utilized in renewable energy systems such as wind and solar power inverters to convert the DC power generated by photovoltaic panels or wind turbines into grid-compatible AC power. 5. Uninterruptible power supplies. UPS three-phase VSIs are integral components in UPS systems, ensuring a smooth transition from grid power to battery power during power outages and fluctuations, maintaining continuous power supply to critical loads. Simulating a shunt active power filter (SAPF) based on the synchronous reference frame (SRF) theory involves using specialized software tools like MATLAB/Simulink or other power system simulation platforms. Here, I'll provide you with a step-by-step guide on how to set up a basic simulation using MATLAB/Simulink for a shunt active power filter employing the SRF theory. Step 1. Model the power system. Create a Simulink model and set up the power system you want to simulate. This includes the nonlinear loads, source, and the connection point for the SAPF. Step 2. Implement synchronous reference frame transformation. 1. Implement the SRF transformation block in Simulink. This block will transform the three-phase signals, currents or voltages, into the DQ rotating frame. 2. Extract the positive sequence components, fundamental frequency components, in the DQ frame. This step filters out the harmonics and other unwanted frequencies, leaving you with the fundamental components of the current or voltage. Step 3. Generate reference currents. 1. Determine the reference currents required for compensation. This might involve calculating the harmonic and reactive power components that need to be compensated. These values can be based on the detected harmonics and reactive power extracted from the SRF transformation. 2. Generate the reference currents in the DQ frame based on the calculated values. These reference currents represent the compensating currents needed to mitigate the harmonics and reactive power. Step 4. Implement control algorithm. 1. Design a control algorithm, such as a PI controller, to calculate the compensating currents. The controller should compare the reference currents with the actual currents in the DQ frame and generate appropriate control signals. 2. Implement the control algorithm in Simulink, using blocks like PID controller or transfer function to create the control logic. Step 5. Inverter model. 1. Model the voltage source inverter (VSI) that generates compensating currents. Use appropriate semiconductor switch models, IGBTs or MOSFETs, to create the inverter circuit. 2. Implement the control signals from the control algorithm to modulate the switches in the inverter, generating the compensating currents in the three-phase system.